Welcome friends. In this lecture session we are going to learn about the minimum and non-minimum phase systems. So the points we are going to cover under this heading are minimum phase system, the transfer function of minimum phase systems and how the response is observed. Also the non-minimum phase systems, the corresponding transfer function and how the response is observed. As it is seen that many of you are hesitant about the body plot of second order transfer function model. So here I have come with a quiz of second order transfer function model. So the quiz is error. Quiz is error at the corner frequency, error at the corner frequency of a second order system model is, you will get four options in this. First is 1 decibel, second option is 3 decibel, third option is -1 decibel, and fourth option is -3 decibel. So you have to find out the correct answer. So here I am not going to discuss with you about the error, but I will advise you to go to the lectures back and find out what should be the error of the second order system model at the corner frequency. So with this brainstorming, let us start the today's topic. First, to start with the minimum phase systems. So what are minimum phase systems? As a system we are studying in the control theory so far, all these systems are minimum phase systems because a system model with stable poles with all the zeros on the left half of the S-plane will define a minimum phase system. Because if all the poles and zeros on the left half of the S-plane, then if you find the phase of the system, we'll see that the phase calculation will give a value which is the minimum value. This is in comparison to the other topic, which is the non-minimum phase system, where we'll understand that the phase is a bigger amount, so that is a non-minimum phase system. So such a system model with all poles and zeros on the left half of the S-plane defines a minimum phase system, and the transfer function will be given like this. The transfer function gs equals to s plus z1, s plus z2, like this. So s plus p1, s plus p2, like this, where we assume that all zi's are greater than 0 and pi's are greater than 0, so that all poles and zeros on the left half of the S-plane. So for your convenience, let me write down the definition of the minimum phase system. This is a system model with stable pole. So that is understood. We are speaking about the stable poles. Stable poles means poles on the left half of the S-plane with all zeros in the left half of the S-plane we'll define a minimum phase system model. A minimum phase system model. So for a minimum phase system model, let us see how in the time axis it should behave. It is the time axis. So let us assume that we are going to give a step input to the system. I am taking a delay initially from 0, then I am giving a step input like this. So the system will have a step input like this, and then I will draw its response. So as long as input is there, output is also 0. So once input comes, then output is coming like this. So here this is the output, this is the output, and this is the input, this is the input. So we can see that there is no delay, actually no delay between the input and the time the response starts appearing. So such a system will form the minimum phase systems. So now we'll see how the non-minimum phase system will look like. So let us understand first what is a non-minimum phase system, because we're speaking about the systems that should have stable poles. So again, in a non-minimum phase system, the system should have stable poles with at least 1 0 in the right half of the S-plane, and such a system will define a non-minimum phase system, because the system should be stable by poles. So all the poles are on the left half of the S-plane, and there should be at least 1 0 on the right half of the S-plane, because when there is a 0 on the right half of the S-plane, such a system will behave differently from all such systems where we have studied. So if we go to the real world of control systems, I am telling you that in 99% of cases the system will have a non-minimum phase response. So let us understand the theory, then I will demonstrate you physically what happens when the system is non-minimum phase system. So as such, this system has stable poles but unstable zeros and exhibits non-minimum phase dynamics. So let me define it first. Definition is a system model with stable poles and with at least 1 0 in the right half of the S-plane. We'll define a non-minimum phase system model. So such a system has stable poles, but unstable 0 or zeros, and exhibit non-minimum phase dynamics. Non-minimum phase dynamics. So then we have GS, the transfer function, is equal to S plus Z1 S plus Z2, like that, with one of the zeros on the right half of the S plane or more of it. So we can say this is Zn minus 1 S minus Zn, like that, divided by S plus B1 S plus B2, like that, where Zi is greater than 0 and Pi's are greater than 0, like that. So because of these zeros, this is a system with RHP zero dynamics. So how the response should come? Let us see the response of it. You have the response axis, then the time axis, and then the step input I am going to here for normalized input output system. So let me give the input first. So I am giving the input, step input first, then the response. So initially, when there is no input, no output, as soon as the input comes, you see the response of this. Like this. So we can see that this is the output, this is the output, and this is the input, this is the input, and here you can find a delay and reverse response. Reverse response. So because of the RHP zero dynamics, there is a reverse response, and which is same as the delay of the system, because if you have a system with a zero like S minus Z, so this can be approximated to a delay term. So we can say that this is approximated to a delay term. So whenever there is RHP zero dynamics in a system, so we can say that such factors, RHP zero factors, are equivalent to the delays equivalent to such factors are associated with the system. So I'm giving you a practical example of this. So you have an aircraft. I'm showing you the top view of this aircraft. And this is these are the two wings, left and right wing. and this is the tail. So what happens when the aircraft is trying to take a right turn? So gradually, because the center will take the right turn like this, but you will see that the tail will have a left turn. They will have a left turn. So this is because of the RHP0 dynamics. RHP0 dynamics, the tail will take the left turn. Similarly, if you have a bicycle, and you have a carrier over here. So if the cycle takes the right turn, you will understand, you will have a feel that the carrier is moving towards the left. So this is again because of the RHP0 dynamics. So such examples are very common in nature, and because of such RHP0 dynamics, designing a controller for such systems is extremely challenging and difficult, and most of the times we have to go for certain advanced control system designs which are beyond the fundamental elementary control system designs. That is the uh, syllabus which you are going to learn in this course. Beyond that, we need to adopt some other technique to tackle such RHP0 dynamics. So RHP0 dynamics are very much practical situations that we encounter while designing the controller, but in our syllabus we are giving you just an introduction to this, so that who are going to design a practical system, they should keep such idea in their mind. So based on these two topics, we will have a quiz. So let us have the quiz. A non-minimum phase system, non-minimum phase system has, number one, stable poles and stable zeros. Stable poles and stable zeros. Such questions can be asked in the competitive exams. Second, unstable poles and unstable poles and stable zeros. Third option is stable poles and unstable zeros. Stable poles and unstable zeros. And fourth option is unstable poles and unstable zeros. Unstable poles and unstable zeros. So this is up to you to answer this question. I am not going to share the answer to this question. Based on the knowledge shared in this lecture, you will be able to answer this question. So this much is for today, and in the next lecture we'll come up with the stability of control systems. So this is the textbook we refer. However, today's topic has been taken from other textbooks, which basically I have referred during my research work, because my research work is related to the non-minimum phase dynamic systems. So these are the two reference books one can refer to. And if this lecture is useful for you, please like the video and subscribe the channel and set the bell icon for further notifications. Thanks for your patient listening.